Good afternoon, everyone. My name is Carlos Javier Quimbiulco, and we are Group 9. Today, we will be presenting on our project on magnetic resonance fingerprinting, MRF for short. In our project, we implemented a 2D MRF simulator to replicate the MRI process by simulating the steps of data acquisition, pattern matching, and property visualization. Our presentation will be divided into the following sections, which are introduction, conventional MRF, low rank MRF, MRF using structured low rank matrix completion and subspace projection, the results of our simulation, and our conclusion. First of all, we would like to start with introduction, which is with what is MRF? MRF is an innovative MRI technique that combines advanced data acquisition with dictionary generation into pattern recognition to map different tissue properties. It has a wide range of applications included, but not limited to brain and musculoskeletal imaging, cancer diagnostics, and cardiac health. Depending on its applications, there are different types of MRF that exist and can be used, including echoplanar imaging MRF, API MRF, MRF ASL, which is used for arterial spin labeling, hybrid MRF, to name a few, but our presentation will focus on conventional MRF, fast low rank optimization reconstruction, FLOR MRF for our low rank MRF, and structural low rank matrix completion and subspace projection, SLSP MRF.
Hi, I'm Xiaoyuan. Firstly, I'd like to introduce the conventional MRF algorithm. In the conventional MRF, the main steps are data acquisition, dictionary generation, and dictionary matching. For data acquisition, firstly, we generated parameters. By varying the acquisition parameters, unique signals are generated from different tissue types, and the dictionary entries are created by simulating the acquisition sequence on a range of parameters, demonstrating different biological tissues based on the block equations. Here is why we could use a dictionary to recognize different tissues. Each tissue type has characteristic T1 and T2 values, and thus each signal evolution has a different types, which confirms that it is possible to satisfy this fundamental assumption in MRF. The dictionary matching contains these steps. However, although the conventional MRF has a good performance after undersampling, it cannot perform well at a very low undersampling rate. This undersampling causes special artifacts that hamper the ability to accurately estimate the tissue parameters. To solve this, the FLOR exploits the low-rank property of the temporal domain on top of the well-known sparsity of the MRF signal in the generated dictionary domain. The algorithm is shown here. Firstly, initialize the parameters. X is the signals processed after block equation, and Y is an undersampled Fourier transform of image frame. Then repeat M times. Each time enforce data consistency with the mirrored case-based samples through gradient descent at first, and then do the low-rank projection and upgrade the X. The aim is to make the reconstruction better. We can see that the reconstructed image is clearer and the MSE between the reconstructed one and the original one. This is the gift. Then do the dictionary matching. This is the difference of performance between conventional MRF and FLOR and the error maps. FLOR outperforms the conventional MRF at low sampling rates. It exploits the temporal correlation in the data, and FLOR uses an iterative optimization process that includes gradient descent for data consistency and singular value decomposition to enforce low-rank constraints. This process suppresses artifacts, ensuring that the reconstructed signal remains clean and closer to the true signal evolution before matching it to the dictionary. By reducing dependency on large dictionaries and filling in missing case-based data through low-rank projection, FLR achieves significantly more accurate reconstructions even under aggressive undersampling conditions, where the original MRF often fails due to incoherent artifacts. We can also find that FLR deals well with motion, but we then notice when the undersampling rate is even lower, like 6%, FLR performs bad.
Hi, I'm Siqi Wang, and I'm going to introduce SLSP method, which is short of MRF reconstruction using structured low-rank matrix completion and subspace projection. In this method, it combines structured low-rank matrix completion with subspace projection in a two-stage recovery algorithm. The first stage is structured low-rank metric completion. This stage firstly models the space-time MRF matrix as a 3D piecewise constant function. Then it maps first-order partial derivatives of measurements into a structured low-rank Topli's matrix. And then it implies a half-circulant approximation for efficient optimization. The second stage is subspace projection. It projects the reconstructed spacetime matrix onto a dictionary subspace to refine multi-parametric estimation. And then it utilizes the Moore Penrose pseudo-inverse for projection and optionally an orthonormal basis to reduce computational cost. And then let's turn to our results. After simulating these methods, the reconstructed images are obtained as follows. The reconstructed images using the conventional MRF method shows some blurring around the edges. And the reconstruction results for FLOR and SLP method are comparatively better. Though their outcomes are visually indistinguishable, these results are based on a 15% sampling ratio. So to further compare the reconstruction performance of different methods, particularly between FLOR and SLSP, we generated aerial maps and calculated the goodness of fit for each parameter map using the normalized mean square error as the cost function. And also, we conduct experiments using 6% sampling ratio. And here's the reconstructed images, and here's the aerial maps. Then we can find that as the undersampling ratio increases, all the methods obtain improved reconstructed image quality, and FLOR and SLP have more significant improvement compared to the conventional method. When using a lower sampling ratio of 6%, the SLSP method is better than the other methods. That may be because compared with FLOR, the SLSP method combines the structure low-rank parallel and the subspace projection model, which can obtain a better performance. Then we simulated motion artifacts in imaging data to test and compare different MRF reconstruction algorithms. In this process, we introduced both horizontal and vertical motion to the original image sequence, and motion alternates between horizontal and vertical directions every specified number of frames. That's because we aim to evaluate the robustness and accuracy of these reconstruction methods under realistic conditions. And here's the result of motion simulation. When we chose motion interval equals to 100, we can gain these results. And to better compare the method, we also analyzed the arrow maps both with and without motion. The results show that the goodness of fit decreases for all methods when motion is introduced. However, the decline in performance for FLOR and SLSP is slightly smaller compared to the conventional MRF method. Additionally, the reconstruction performance for T1 and PD is less affected by motion compared to T2. And here's the result for when we chose motion interval equals to 50. And the results are similar. And here's the result for 6% sampling ratio with motion.
Finally, in conclusion, this project evaluated different reconstruction methods for magnetic resonance fingerprinting under undersampled and simulated motion artifacts. Conventional MRF, low rank MRF, in our case FLOR, and structural low rank matrix completion and subspace projection SLSP MRF methods were compared. All methods improved the reconstruction quality as the undersampling ratio increased, but FLOR and SLP outperformed the conventional MRF. In our case, SLSP delivered the best results, especially at low sampling ratios, which in our case was 6%. We also did the motion simulations to incorporate alternating horizontal and vertical movements to replicate the real-world imaging challenges, highlighting SLSP's robustness in such conditions. This is our reference list, and thank you very much for listening.